Day everyone. I, Carl Emmanuel Urfe, along with Sedi Araula, Clark Velos, William Wallace Lamberta, Kenneth Rex Dahan, and Kim Ayan Melanchon are here to present to you our recently conducted vibration analysis of an airfoil of a simple airplane drone wing. So, what is an airfoil? An airfoil is the cross-section of the wing of a plane. Its main job is to provide lift to the airplane during takeoff while in flight. But it has also a side effect called drag, which opposes the motion of the airplane. The amount of lift needed by a plane depends on the purpose for which it is to be used. Heavier planes require more lift, while lighter planes require less lift than heavier ones. Thus, depending on the use of a plane, airfoil section is determined. The particular wing design also depends upon many factors like size, weight, use of the aircraft, our desired landing speed, or our desired rate of climb. So next, for our system model, we have a simple airplane drone wing, which would be modeled and simulated using the engineering software SolidWorks 2018. For our dimensions, we have the wing length, which is 1 meter, our root and tip length, which for the root is 0.397 meters, and for our tip, we have 0.1756 meters. For our thickness of the surface taken, it would be 3 millimeters. For our geometric twist, we have 1.5 degrees. Our incidence twist, we have 2.5 degrees. And our dihedral twist, which has 5.5 degrees. For our aspect ratio, we have 7.448, and our taper ratio would be 2.271.
So next, we have the material selection. So for the name of our material, we have aluminum 24T3, which has the property of the following: elastic modulus, which is 73 gigapascal, the Poisson's ratio, which is 0.33, the tensile strength, which is 345 megapascal, the thermal conductivity, which is 121 watts per meter Kelvin, the density, which is 2,750 kilogram per cubic meter, and the shear strength, which is 283 megapascal. So why using aluminum 2024 T3? So aluminum sheet plate 2024 T3 or T351 is normally used for aerospace, automotive, machine, and industrial application. 2024 aluminum is one of the strongest aluminum alloy, though with slightly less corrosion resistance. So in this case, we did not add other features that act as the damper, only the material itself. Aluminum has the ductile fracture behavior at all temperatures. The properties of many metals change when exposed to very low temperature. These changes occurs in strength, toughness, brittleness, and durability. Aluminum is known to sustain or even improve both ductility and toughness at very low temperature. So next, we have the meshing. So in the right part of the screen, we have the presentation of the meshing of our design. Unit cell size of a mesh is very important. The accuracy of the result of the experiment depends on the element size of the mesh. Finer element size enhances the precision of the result, but this requires higher computation power and consumes more time. As the total number of nodes increases with the increase of total number of element size, the simulation requires to solve all those points, keeping the computing power of the computer used. The mesh was generated. Here are the inputs, element size parameters, which is the maximum element size of 0.012 meter, minimum element size of 0.02 meter, the maximum element growth rate, which is 1.5, the curvature factor, which is 0.5, the resolution of narrow regions, which is 0.8. This generates 147,864 number of domain elements, 17,160 number of boundary elements, and 294 number of edge elements. This provides an acceptable accuracy of results, consuming a moderate computation time. So next, we have the boundary condition. At the root of the wing, frictionless fixed support was given similar to a cantilever beam, which is marked black in the figure presented. Frictionless support places a normal constraints on the entire surface. Transitional displacement was allowed in all directions. Next, we have the existing loads applied to the system. So here we consider two forces, which are the lift force and the drag force. Here, the lift force is named as pressure 1. Why pressure 1? We consider the lift force as the force 1, and while solving the force, we will consider pressure, so we named it pressure 1. So lift force is a fluid flowing around the surface of an object exerts a force on it. Lift is a component of this force that is perpendicular to the oncoming flow direction. It contrasts with the drag force, which is component of the force parallel to the flow direction. Next, we have the sideways force, which is named as pressure 2, or the or the drag force. So the drag force is an aerodynamic force that opposes an aircraft's motion through the air. Drag is generated by every part of the airplane, even in the engines. Drag is generated by the difference in the velocity of the solid object and the airflow. There must be a motion between the object and the airflow.
The next slide is the existing loads applied to the system, natural, lowest, and highest frequency. There is natural frequency at every iteration. So there are 15 iterations. This means that there are 15 frequencies where our mode 1 is the lowest frequency and the highest frequency is mode 15. And this tells us that the more you add modes to the frequency, it will increase and the number of cycles of vibration that makes the airfoil more prone to deformation. These are the list of resonant frequencies where it is known that the natural frequency where it tends to vibrate at the highest amplitude. These examples, the shattering of the glass where it reached its limit of vibration, then it shatters. This tells us that when the airfoil reaches its maximum vibration, it may deform or break into parts. Next is these are the forces acting on the system of our airfoil. The nets wrapped on the airfoil are called meshing. The arrows below on the airfoil that points upward motion is the lift force that is directly opposing the weight of the airfoil. Then the arrows pointing to the back motion of the airfoil is the drag force, where this is the acting opposite of the relative motion of our airfoil.
Forces. Here in our page 12, we have different forces here on different plane of our airplane wing. For the reaction force, in x-axis we have negative 109.738. This force is caused by the sideways movement of our airplane or our airplane wing. For the y-axis, we have negative 1,992.59. This is caused by the lift force. So for the z-axis, we also have 5,237.96 caused by the drag force. If we get our resultant force, we get 5,605.24. And also for the reaction moment, we don't have any values given here on different planes, especially our airplane wing does not rotate. Here we have the tabulated data of our stresses, the level of stresses or the values of stresses in the different nodes of our airplane wing. As we go back on the page 11, we have here different meshes on the different sides of the plane. So these nodes are we only choose 20 nodes since our now the number of our meshes is close to infinite. So vibration caused by the wind force. Vibration caused by the wind force is also known as wind-induced vibration. It's a dynamic response of engineering structure to the vibration caused by the action of fluctuating wind. So here we have our amplitude 1, or in our simulation, here with the 114.819 Hertz, we can see here that the strongest part of the airplane wing is the blue one, or the one close to the fixed part of the airplane wing. So here indicated in this simulation indicated here that the red is the weakest one or the most fragile in the airplane wing to vibration, and the blue one is the strongest part of the airplane wing.
So for our second simulation, or amplitude 2, so it has an amplitude of 429.126 Hertz. So it has a minimum at node 3 and a maximum of node 1. So in here, as mentioned before, the blue color represents it is not prone to stress. So in this simulation, it is less likely to receive stress or to be affected by stress. So as we can see, near the fuselage or the body of the airplane, the part of the wing, this part of the wing is less affected by the stress. So as we can see also that the red part shows its proneness to receive stress. So in here, we see that the red part or the tip of the wing received the most stress. And also, it is good to note that in the middle of the part of the wing, as we can see, it bended or it curved due to the fact that it bended because of the stress difference between the tip and between the two tips of the wing. So because of great stress applied to the tip of the wing, on this part of the wing, it curved or bended, or it is commonly known as a wing flex. So for our third simulation, which is affected by an amplitude of 433.754 Hertz, as we can see, it is pretty similar to our amplitude 2 because it shows or it portrays a wing flex. But in here, it shows a greater bend or a greater wing flex. So it is also similar because near the fuselage or the body of the plane, that part of the wing is received less stress in comparison to the other tip or the tip of the wing. So just like in simulation 2, the tip of the wing also received the most stress. And the middle part also got bended because of the stress applied in the tip, because this part of the wing resisted or hasn't received much stress, and because of that it created a bending force which bended the wing or flexed the wing. And it also showed that at the middle it portrayed an average or received an average pressure or stress. So in our fourth simulation, with an amplitude of 698.907 hertz, with a minimum at node 3 and a maximum of 114 at node 114. So in this simulation, it is different from the previous simulation, because as we can see, the wing haven't received or isn't affected much by stress. So as you can see, almost all part of the wing is color blue, which means it isn't affected by the stress, or it isn't affected much by the strength. So meanwhile, at our simulation 5 or amplitude 5 with a value of 993.601 hertz, with a minimum at node 3 and a maximum of 11,446 node. So just like the previous simulation at node 2 and at amplitude 2 and amplitude 3, excuse me, it also showed that near the fuselage, it didn't receive much stress, but in here we can see that there are 3 parts which didn't receive or is less affected by the stress. So in here we see that it is also similar to simulation 2 and 3, because the most affected by the stress is at the tip. So as we can see, it is also quite unique because it created 2 wind flex or 2 bends in or 2 curves in the wing. So it is because of the reason that there are 3 parts of the wing that is not affected or is less affected. And because of this, because the pressure or the stress received by different parts of the wing, it caused more bending, which as we can see, it is in the middle of the airplane, which received less or little amount of stress.
And next is the tabulated data of the modal analysis. So the modal analysis is a common method used to investigate dynamical behaviors of mechanical structure under the dynamic excitation. It is used to determine dynamic characteristics of a system such as natural frequency, mode shapes, and etc. Emitted noise reduction from the system to the environment is enabled by the modal analysis. It helps finding out the reasons of vibrations which cause damage on the system and used for reducing it. In short, one can improve the performance of a system by using modal analysis method. And for the tabulated data of the modal analysis, we get, for the first frequency number, we get a 721.43 rad per second with a frequency of 114.82 hertz in 0.0087094 seconds. For the second frequency number, we get a 2696.3 rad per second with a 429.13 hertz in 0.0023303 seconds, and so on and so forth. And for the next slide is the graphical data of modal analysis. So as we can see on the graphical data of modal analysis, for the frequency versus the number of modes, we can see that the number of modes increases as the frequency of the system is also increasing. It is the same as what is being shown on the tabulated data of the modal analysis. So as we can see on the graph, as the number of mode increases, the frequency is also increasing. So therefore, the natural frequency also increases. For the mode number 1, we get a frequency of 114.82 hertz. For the mode number 2, we get a frequency of 129.13 hertz. For the number 3, we get a 433.75 hertz. For the number 4, we get 698.91 hertz. And for the frequency number 5, we get a 993.6 hertz. And the mode and the frequency is also increasing. And for the next slide, during wing vibration, all motion parameter oscillates, which result in unfavorable working condition for many onboard systems. For instance, the autopilot system. The vibration badly influenced the working environment for crew and travel comfort as well. Wing vibrations have also significant effect on the airframe, loading, and durability. Premature wear and tear of the wing joints in the fuselage, suspended devices, and control surface mountings in the wing are caused by varying loads. Additional forces occurring on ailerons as a result of wing deflection along the plane's normal axis might result in larger wing deflection and loads in the lateral control system. So up next is the simulation of the modes of the system.